Hello, Internet! Today, finally, we are back to the basics and we are coding. We are coding on a Jupyter Lab. We have Python. And here we go. And our topic today is tokenizers. NLP, BERT, tokenizers, for example. So let's start and stop. No, you have to understand at first the basics. No, don't do this to me. I want to code. No, there's no coding now. So, to understand what's going on, at first, where are we? NLP. You want to train on an AI system. You have your BERT model designed. You know what the training parameters are. You have a corpus of text designed for you, normally sentences. And then I always make the same mistake. I just let the system choose a tokenizer and I just start with the input in my data pipeline by not carefully choosing the tokenizer system, the vocabulary that I use specific for my corpus of text. And this is a mistake I want to show you and I want to learn from my mistakes. So here we go. At the data input pipeline, our data pipeline that feeds our BERT model, that feeds our NLP deep learning model whatsoever, the very first step is, if you have your sentences, second point, choose your tokenizer architecture. Then you train your tokenizer on your specific corpus, and you get a specific tokenizer for your text corpus, something optimized for your task on your specific text, not trained on all the contents of Facebook, but if you're working in theoretical physics or chemistry or material science or biology or virology, you have specific text documents and you have a specific vocabulary, with specific terms that you need that the system learns later on. And if you do not get it right in your input pipeline, you can optimize your design, your model, your BERT model later. You can run 1,000 epochs and it will not converge because you get it wrong at the very first data input pipeline. So do not make my mistakes. And now here we go with coding. Finally, yes, we can go with coding now. Come on, dismiss. So this is it. We are here. Them beautiful tokenizers. Here we go. And you might say, what is tokenization? Now, very easily, give them a character sequence, like sentences, words in sentences, and a defined document unit, like a paragraph, a book, a publication, whatever. 1,000 publications. Tokenization is the task of chopping it up into pieces, called tokens, so little small tokens, perhaps at the same time storing away certain characters, such as punctuation. So this is what we do. We convert our human readable sentences, books, document, paragraphs, preprint, publications into machine learning numerical representations, matrix, tensor. So therefore that our BERT system can apply the tensor algebra to optimize our system. So therefore, we go from transformers, import, pipeline, tokenizer, auto model for sequence classification, TensorFlow, everything. And again, theory. And you say, no, I hate theory. I know, but listen, just 4 points and we are done and we can code, okay? So here we go. Our tokenization pipeline, our data input pipeline to our NLP system, to our deep learning system, to everything that's so beautiful. 4 steps. At first, normalization. Very easy. It's just make your input data clean. This is it. Remove some white space. Remove some accented character or lowercasing. Unicode normalization. Very easily done. Second, pre-tokenization is the act of splitting a text into smaller objects so that you can handle it. For example, you split your text in words, and then your final tokens will be part of those words. Beautifully. Now to the most complex parts, and this is models. once your input text, your sentences are normalized and pre-tokenized, the tokenizer applies the model, and now the tokenizer model, not the AI model, the tokenizer model under pre-tokens. And currently, our Hugging Face Tokenizers library supports 4 different models if you want. So there's a byte pair encoding, there's an unigram encoding, there's a word level encoding, the most simple tokenizer model. And then, like if you're familiar with BERT, there's a word piece model. And of course, the final version is post-processing. You have your special tokens that you want to end, especially in BERT. You're familiar with the CLS, the classification token, the SAP token. This is what we are going to do. So the recipe is, our tokenization pipeline has 4 parts. Normalization, we clean it. Pre-tokenization, we define the tokens that make up our vocabulary. We have a specific model for our tokenizer, and then we do just add our special tokens so that the BERT model, our deep learning model, is able to process the data. This is it. Finally, great. So, first step first, the British Butler full service, everything done for you automatically by the beautiful people of Hugging Face. So, we are back in the game again. Let's talk Hugging Face full service, the British Butler model, to define my tokenizer. So what it does, it goes automatically, connects to Hugging Face, downloads the model for you, and this is what you get. You get a fixed tokenizer. It's a pre-trained tokenizer, and it's a fast tokenizer. It tells you, hey, done in Rust, so perfect, ultra fast. The name is BERT-based, uncased. My vocabulary size are 30 Ks. My model maximum length is 512. I'm fast, yeah, it's true. My padding size is on the right. My special tokens are SAP, PAT, CLS, and mask. So perfect, exactly what we want. And now we apply this tokenizer to get the perfect tokenization. And if you do this on a specific sentence, you will see the tokenization is now machine readable. 101 is your special token, and then you have the word part tokenization happening. And 102 is again a special token. And if you want to say, hey, great, so this is the input to my machine learning model, to my deep learning model, it's great. But can you show me how did it qualify going into this? And here we have it. We have, in quantum mechanics, a probability amplitude is a complex number used in describing the behavior of systems with the R. Now here it happens the first time. The specific term modulus is not within the vocabulary system of this specifically trained model, BERT-based uncased. So what it does, it splits it in mod and #s ulus. But the rest it has in its vocabulary, all the other words in the vocabulary, squared of this quantity representing a probability density. So this is beautiful. This is what we need. Because now what it does, it takes our sentences with our special token at the beginning and at the end, and it used really, it knows the word quantum, it knows the word mechanics, it has transformed it in a numerical presentation 1999 and 8559 and whatever. So, and you can be sure that the words quantum, like say on probability, are part of the vocabulary, are learned, and therefore this is the way you want to have your tokenizer to behave. This is great. Training a tokenizer is a statistical process that tries to identify which subwords are the best to pick for a given corpus, and the exact rules used to pick them depend on the tokenization algorithm. Great. And to show you here, I've chosen a really complex 2-sentence system. And if I apply some tokenization, I get this back. And you might say, hey, wow, this is quite a lot of numbers. I mean, are you sure this is the best representation of my 2 sentences in a numerical value system with a specified vocabulary? And if you check it, you find that the tokenizer has been trained on this text, wiki text 103, and the model used for the tokenization, it was a byte pair encoding. And if you then take the next step and decode the encoding, you will find that the system sees your two sentences, human readable sentences, in exactly this way, and it encodes the sentences in this subwords structure. So it says in quantum mechanics, and you see even quantum, it divides in 3 parts. So like a child that's learning to read and learning to understand the world around it, sometimes the child spells the word because he does not get the meaning of the word, that this is one entity. And this is exactly what happens here with our AI system, but with just the input encoding. So quantum is split in 3 word pieces. Mechanics even is split in 2 word pieces because our training data set, Wikitext 103, did not incorporate the words quantum mechanics. Maybe it was on art or literature or humanity or I don't know what, but not on my quantum mechanics. So therefore, the system cannot encode my sentences in the optimal way. Probability amplitude. What does it do to probability amplitude? Heaven's sake. Okay, it knows complex. It knows number used in. It doesn't even know describing. It makes describe and bing. And the modulus, I don't want to even talk about the quantity. But let's have a look at Q. Here, Q is here. Then where else is Q? Here. So we have Q in quantum. We have Q in squared. You see, even I do not know where the words, and this is what the system encodes. This is what your BERT transformer models tries to optimize to learn. This nonsense is learned. And then you have Q here in quantity. And so tell me, is Q in quantity close to Q in squared? And is squared close to quantum because Q? You see the problems we run into this, so we definitely have to optimize this. And as I told you, what I want now is this representation. I want this input data representation of my 2 sentences, because if I decode this numerical encoding, I get this. And this is what I want. I get my 2 beautiful sentences in a vocabulary that has been trained on my specific task, let's say physics or chemistry. And now suddenly I have the word quantum in my ability, in my vocabulary. Quantum mechanics, exactly as I wanted. Quantum and mechanics are now words in my vocabulary. And if I check the file, vocabulary text file, I will see that I have a lot of other words not in there, about politics, about lifestyle. But I have all quantum mechanics in my document, in my system, in my vocabulary. So I know if I train the BERT model afterwards, quantum mechanics is there, probability amplitude is there, everything is there. Again, modulus is not there. This is the only where it splits up in hash, but okay, this is a BERT specific topic. But even probability density is there. We see we have here the notation and the comma also separated. Beautiful. I can later take care about this. But this is the vocabulary I want to have. And this is the encoding, the machine encoding. This is my data input that is now ready to be fed into my deep learning NLP system. And this is the optimal input data pipeline representation of my text. So this is exactly what I want. And now let's go back here to our Jupyter notebook. And this is exactly what we get out. And this is the sentence, this beautiful sentence. And you see, if we choose a huge model and BERT base, and not the distilled BERT, but the full-fledged BERT model, can provide us. It has a vocabulary size of 30,000 vocabulary items. It is fast, maximum model length of 512. Of course, you have to take this into consideration. And this is it. Of course, let's do the same now with a fast tokenizer. You have within the transformers, and I will show you the difference between the transformers and the tokenizer library itself. You have distilled BERT tokenizer fast. So let's run through this. If you want to accelerate your calculation, this is what you do. So what you end up now, you have a distilled BERT, so a smaller tokenizer. You still have a vocabulary size of 13,000. You have a maximum length of 512, but it has been trained on a smaller body. And then if you have this sentence and you convert your IDs back to the tokens with your specific fast distilled BERT tokenizer fast, you see that you end up with the same. So even distilled BERT is capable, beautifully doing all the right things to your sentence, and it constructs the perfect vocabulary with a size of 30K, which is sufficient that your sentence about quantum mechanics is represented in the perfect way for your deep learning exercise. Then you can have a look at this. Since we're operating now in TensorFlow, you can have, of course, in PyTorch. But let's say that our tensors and our TensorFlow tensor representation, you see what you get is, you get an input ID from a tensor shape 134. This is exactly your representation. I showed you also in green. Then you have, of course, your attention mask. And this is it. If you want to go on now, and this is now the next step, if you want to train your BERT model, this is exactly how you do it. You define your model, and now we downloaded it from Hugging Face. This is your distilled BERT model, your deep learning model. Just download it, get the model ready to rock and roll. Tells you, hey, you should maybe train it. Yes, that's clear. So we have a transformer model, distilled BERT, ready to go. And then what we do is our encoded input, our beautiful input that we get applying our fast tokenizer on my sentence now. And now I have the model I downloaded with my specific checked encoded input, my sentences. And I can let it calculate. And what I have now as a result, the output of my BERT model now with my optimal input presentation is a tensor in the shape 134,768. Are our hidden dimensions. And you now have exactly this beautiful output from the last hidden state of your BERT model. So you would say, great, this is it. I have everything automized. I just have here all the models, and I have here my full service auto tokenizer. Well, if you want to change something, if you want to alter it a little bit, you have to dig in. And this is what we're going to do now. We are now construct our tokenizer ourselves. Let's say you have a vocabulary file. And this is something you can download or you can train yourself, you can construct yourself. So next easy step is you have a vocabulary file. And the nice people from Hugging Face present us a vocabulary file, especially for BERT base uncased. The vocabulary file I showed you in my last video that is downloadable from Hugging Face. And this is exactly what we do. So we have now the BERT base uncased vocabulary file that the BERT base model was trained on. And we have a look at this. And you see the first, now boring, 1000 lines are not used. And then you have the Chinese character if you want to do some translation. And then finally we come here to the English words. And this is, let's find the beginning. Here's Chinese. I think it's Chinese. I don't know. Sorry if I made a mistake. Then the first word is the. And then you have of, and then you have and then in, and to, and was, and he. And you see these are one of the most used words maybe in your training document. And then you go on and you go on and you find the words when, of, the, there, into, to. And then you have your hash. And your hash hashs are easy. This is when you have to split a word in different parts. And the second and second plus terms are always hash hash. So these are composed terms. This is done if you have a singular and a plural form, car and cars. Cars, the plural term, will be split in car, the singular form, and a hash hash s. So that you always know, hey, what is my singular form? It is car. So you have here hash hash d and whatever, and then you have here even university quite early in the document, and then you have 30,000 vocabulary words. And every word that is in here is learned as an entity, is encoded as a numerical representation, and is optimal for your model. Now we say thanks, clear the outputs. We believe that this is the right model, the right vocabulary for our BERT base model. And now we have two options. We have now the Tokenizer library from Hugging Face, and we have a transformer library from Hugging Face. And sometimes some people mix them up. Now, if you have the Tokenizer library, which is Rust-based and which is quite fast, I would recommend this, using this. You have the BERT word piece tokenizer. And let's apply this. Let's run through this. And you see, you have now a BERT tokenizer model downloaded. This is what we know already. And our model is a word piece model. Remember, going back. We have here now a word piece model, and I showed you the first one was a byte per encoding. So now we have another model. Where are we? Here we go back. And then we encode with this model my sentence. And you say, okay, this is it. We have a number of 34 tokens. We have our attribute identity, type of identity, our tokens, our offset, our attention mask, our special token mask, and the overflowing parameter. And what you can do now is, you can just have a look at this. So your IDs are, again, you have your start special token, and then you have the encoding of all your word pieces. If you want to see the translation in your token from our two sentences, there we have our start token, and then in quantum mechanics, a probability amplitude is a complex number used in describing so beautifully, and our end token. So everything worked fine. Our classical attention mask, since we have just one, was of course 1. And our special token we have at the beginning and at the end. So we have 1 at the beginning and 0, 0, 0, and at the end we have another 1. So this is it. Of course, we have the classical transformer library, where we also have a BERT tokenizer. Now this is an alternative route you can take, but you do not have to take. Let's run through it. And as you know, BERT was trained on 2 primary tasks, and mask language modeling and next sentence prediction. And this is why we have the mask token in our special token repertoire. And then if we have the next sentence prediction, you have to train it. You have a CLS token, the sentence A, you have a separator token, then the sentence B, and a separator token again to tell you, hey, this was it with sentence B. So this is our special token configuration. And you can run through this now from our transformer library. You have your pre-trained tokenizer, defined tokenizer by the system, and you encode here the 2 sentences with our special token again. And then you can say, okay, how does it look like? Yes, beautiful. So even if we use the transformer library, this was the transformer library, we get the same results. Well, exactly how it should be.